Professor, uh, I can't hear you.
Is it good? Is it picking up?
Yes, sir.
Okay, sorry. I think my mic was off. Okay, super quick recap for you guys. We introduced limits last time as limits at infinity. As x gets bigger and bigger, the function value gets closer to L. Thinking of this as a table, if you make, the saying is if you go far enough down your table, then the outputs you get will be as close as you like to this fixed number L. And the limit as we go to minus infinity is you're using negative values getting more and more negative. Graphically, what this looks like, and we had this picture up last time, was if we say look at 1 over x squared plus 1, then in this case, if we look at these limits at infinity and minus infinity, as we go to infinity, that's saying look further and further out to the right, what happens to your graph. And this, while the picture is not great, it'd be better on a graphing calculator or something. This is getting closer and closer to 0. And so that is the value of this limit. As you go further and further out, it's getting smaller and smaller, leveling off at the x-axis there. And the same thing with negative infinity, but the opposite direction. Here we're saying go further and further out to the left, what happens to the graph. And as you get further and further to the left, this is getting lower and lower, leveling off at the x-axis. So this is also 0. The behavior here is also something you've encountered before. This x-axis here is a horizontal asymptote. And if you think about horizontal asymptotes, it's this line where you get closer and closer to it as you go further and further out, and that's exactly what we're seeing in these limits here. So really, horizontal asymptotes are some kind of limit quantity. So y equals L, a horizontal line, is a horizontal asymptote of some function f if either the limit as you go to infinity of this function equals L, or the limit as you go to minus infinity of this function equals L. So an important practical takeaway is anytime that you're asked or you want to talk about horizontal asymptotes, you're really going to be talking about one of these limits at infinity or in minus infinity. And so because of what we saw here, this function has one horizontal asymptote of 0, and it's really because these two limits are both 0. So that one line is an asymptote for both directions. But there can be more things happening with horizontal asymptotes. So for instance, what if we find the horizontal asymptotes of inverse tangent? So this inverse trig function is you take the middlemost part of tangent and you flip it on its side. So the graph of inverse tangent has this shape. Where these two dotted lines are the flipped versions of the vertical asymptotes of tangent. This is up at pi over 2. This one down here is negative pi over 2. So given this function, if we want to talk about horizontal asymptotes, the way to really do it is first you're thinking about these limits, and then depending on what numbers you get, then you can obtain the horizontal asymptotes from that. So if we want the limit as x goes to infinity of inverse tangent, this is saying look further and further off to the right. That's moving up towards this pi over 2. So that's our limit off to infinity. If we go the other way, taking the limit as x goes to minus infinity, now we're going out to the left, we're heading down towards this other line, negative pi over 2, and that's our limit in this case. So in this situation, there are actually two different horizontal asymptotes, depending on which direction you're looking. So to abbreviate even more, the horizontal asymptotes are these two lines, y equals pi over 2, and y is negative pi over 2. And as a observation which we can kind of tell, there can't be more than two horizontal asymptotes. There can be one for either direction, but there just isn't a third direction to potentially have. But you can have one, you can have two, and some other things can happen that we'll keep looking at. Before I go too much further, questions about anything so far? Okay. A lot of horizontal asymptote stuff you've encountered before, so this will be a somewhat quick recap, and maybe looking at things in a slightly different way, but a lot of this will be familiar. Now let me make sure all these chats are just people saying that they can't hear me. Okay. So we can have one asymptote, we can have two asymptote, but we don't have to have any even. For instance, what about x squared, our basic parabola? This doesn't have any horizontal asymptotes at all. As it's going up in both directions, it's not leveling off anywhere. And we can even have kind of a mix behavior. If we look at e to the x, exponential functions have their graphs looking something like this, going up to the right, but on the left, this is where we have some horizontal asymptote behavior. As we're heading off to the left, this is getting closer and closer to 0 as you're moving further and further off to the left. So in this case, we have the limit as x goes to minus infinity of e dx is 0, which gives us that horizontal asymptote of 0. So there can be a lot of different behavior, and these aren't even piecewise or anything, just the two directions can have a lot of different behavior. in the last two examples there, we have that the functions are getting bigger and bigger as you go further to the left and right. And those aren't horizontal asymptotes. But like with vertical asymptotes, we want to kind of describe this behavior using our limit terminology. So the way that we will talk about that, and it's not surprising, it looks like if these are going to do anything, these limits are going to infinity. So the limit as x goes to infinity of f of x equals infinity if the function values f of x can be made and kept arbitrarily large, so you can make the function values as big as you want, and once they're big, they stay big, is what this is saying. And you can make them big by choosing inputs x sufficiently big. So this is the kind of wordier way of saying that these functions, and these two examples are cases where that's happening, you can make these functions as big as you want by looking far enough out to the right. Or if you were thinking of constructing a table, you have x's getting bigger and bigger, and their corresponding outputs, you can make those outputs as big as you want. Pick the biggest number you can think of, and somewhere down the outputs, you will be above that. And once they're big, they stay big. It's not like they get big, and then they get small again, then they get even bigger, and then small again, and then even bigger and smaller. They have this kind of standard, you're getting big and you keep going up kind of behavior. So for instance, in say that e to the x, the limit as x goes to infinity of e to the x equals infinity. And examples like this where limits are infinity, this is why this kind of topic is sometimes called end behavior, because it's not all horizontal asymptotes where you actually level off. But we do want to describe what's happening as you look further and further to the right or left. What I'm not going to write out, but you can sort of imagine, and we'll look at some pictures exemplifying this. So similarly, we can define some other variations of this, which introduce some negative signs in there. So we can have something like the limit as x goes to minus infinity of f of x equals infinity. This is what's happening over here to the left. This is saying as you go further and further left, you get bigger and bigger. And that's what's happening here. As you're heading out this direction, the left half of the parabola keeps going up. We can also have the limit as x goes to infinity of f of x equals minus infinity. This would say as you're going further right, you're going down. And then the last combination of negative signs is you can have the limit as x goes to minus infinity of f of x equals minus infinity, which is saying as you're going left, you're going down. So for example, if we look at negative x cubed, so negative x cubed has this shape right here. Positive x cubed is a flipped version where it's going up to the right and down to the left. The negative, when you multiply a function by a negative, it flips the graph upside down. So in this case, we have some of these other options. In this case, what's going on? The limit as x goes to infinity, minus x cubed is going down. So this guy's negative infinity. We can also ask what happens as we let x go to negative infinity, which means what happens as we're going left. Well, this one is going up. So this is positive infinity. That looks too much like a negative sign. Equals. Quick questions about any of this? Again, perhaps familiar, but you weren't talking about it in terms of limits when you've seen it before. So it's just making sure that we're all together. Okay. So one observation that you may be seen, maybe not, is if you're talking about power functions, so power functions being power of x, maybe with a coefficient multiplied, the shapes of the graphs are basically x squared going up in both directions, or x cubed going opposite directions. And the breakdown is basically, is the power even or odd? Even looks like x squared, odd looks like x cubed, and you have a negative or positive number in front. Positive is kind of a standard version, negative flips it upside down. So I'll lay that out more carefully in sort of a flow chart thing. But that observation on its own is pretty good. But what's even better is that will actually tell us what happens with all polynomials in general. So not just a single power, but a bunch of powers added up. So first up, here's this important fact. If a polynomial p of x, so powers of x added up with constants in there and all whole numbers, if this has leading term a to the xn, here leading term means biggest power. Often this is the first one reading from the right, but not always for whatever reasons there might be, but this is the biggest power. Then p of x and its leading term have the same end behavior, meaning p of x and the leading term have the same limits as you go to infinity or minus infinity. So as a specific example, just to emphasize this, x to the fourth minus 10x cubed plus 100x squared minus, I don't know, pi over 16. Really awful polynomial? This has the same end behavior as its leading term, the one with the biggest power, x to the fourth. With the reason why being, if you were to pick very large x's, positive or negative, and put them in here, if you compare the numbers a billion billion to the fourth and a billion billion cubed times 10, raising it to the fourth power is so much bigger. It's got an extra factor of a billion billion in there. It's just so much bigger that compared to the rest, these numbers they're tiny, they don't matter. So what happens is when you're picking x's so huge, the bigger power just dominates everything and it decides what happens. And the way that you can kind of think about it is, well, another way is x to the fourth is like a version of x squared. This more complicated version, it might have a lot going on close to 0 or for smallish numbers. But a way that you can picture it is saying there's some kind of box with the interesting stuff happening. Interesting for most other reasons. Zeros, intercepts, high points, low points, things like that. But having the same end behavior as x to the fourth, what that means is that eventually our little guy with its arms here, I guess, it's saying whatever is happening in the middle, you will eventually get past it. So you're going up to the right and up to the left. So for polynomials, it's all about that leading term. So we want to make sure that we can easily determine what is happening with those power functions. So if we want to talk about end behavior of ax to the n. So the breakdown is you have either the power is even or the power is odd. And then it splits into two cases. Is the coefficient in front positive or is the coefficient in front negative? And if you're even and positive, you look basically like x squared. What actually happens if you have higher powers of x, you're a little flatter on the bottom and you're a little steeper on the sides, but you still look like this. And if you multiply by a negative number, you're this, but flipped upside down. If n is odd, you have the same split. You want to know if a is positive or a is negative. If you're positive, you look like normal x cubed. Again, if you pick if n gets bigger, you're a little flatter close to 0, a little steeper outside of 1 and -1, actually. And if you're negative, or if your coefficient in front is negative, you're this but flipped upside down. And then if your question is, what are certain limits at infinity or minus infinity, picture the right graph and then see if this corresponds to infinity or minus infinity. So for polynomials, we can totally understand what they are doing. It all comes down to the leading term. And in this case, there are a few options, but there are a few basic shapes, and then we pick if it's infinity or minus infinity. But in particular, for polynomials, their end behavior is always infinity or minus infinity in the two directions. They don't have any horizontal asymptotes at all. Which is good, I guess, but also not very interesting. So now we want to start branching out and seeing what are some other functions whose end behavior we can analyze. In particular, a big class will be rational functions, so polynomials divided by other polynomials. There's a lot more that can happen, but we can also completely determine what their end behavior is. So the first kind of additional fact we'll add on is the following. If a limit has the form k over infinity, so the top is some number, the bottom is going to infinity, then the limit you're looking for is going to be 0. So this is a little like when we were talking about vertical asymptotes. If your form is a number on top that isn't 0, but the bottom is 0, you know you have an asymptote. There you have to worry, is it going to positive or negative infinity? In this case, it doesn't matter. You're just 0. There is no positive or negative 0. What also doesn't matter is this infinity on the bottom. I should add this in. It can be either positive or negative. So what's happening is if your top is fixed and you're dividing by larger and larger numbers, dividing by a big number gives you a smaller number. And it doesn't matter if you're dividing by a big negative number or positive number. It would matter in maybe the table, do you have positive or negative numbers? If your limit is 0, that's all you're really keeping track of. You're getting close to 0, not worrying about if it's positive or negative along the way. So for instance, we'll see a couple examples. If we take the limit as x goes to infinity of 2 over e to the x, a lot of these limits, the work involved will be really looking at the pieces separately and seeing what those limits are. Constants, like before, don't go anywhere. A limit of a constant is just that constant. For e to the x, the way to really go about it is mentally picture the graph. And, well, I guess one way is just remember the specific fact. The limit as x goes to infinity of e to the x is e to the x. The way that I do it to try to minimize the quantity of things that I need to memorize is that really e to the x has this shape. And so this limit has the form 2 over infinity, because e to the x is going to infinity. And that means that this limit is 0. The top is 2, the bottom keeps going to infinity, and so the fraction overall is going to 0. So there's not a lot of work involved here. The work is probably just writing down this is the form of the limit and then interpreting it to get 0, but it does require you knowing that e to the x goes to infinity. If we try another one, let's go to minus infinity of 3 over x to the 9th. Here again, if we think about the form of this, the top is fixed, so that's just 3. The bottom is x to the 9th, so that's odd. It just has a 1 in front, so it's positive. It's got this shape. And if we're going to minus infinity, we're going down to minus infinity. So the top is fixed. The bottom is going to minus infinity. The minus on the bottom doesn't affect that the limit is going to be 0. Dividing by a big negative number is still getting closer and closer to 0. Questions about either of these guys? So the top also doesn't have to be fixed. It, I guess, often is, but not necessarily. So if we have something like the limit as x goes to infinity of inverse tangent of x over x squared plus 1, here we still want to look at the top and bottom separately. On the top, this was one of the graphs we looked at earlier. This is that sideways tangent, and this does have a horizontal asymptote. So it's still moving, but inverse tangent does level off at pi over 2 as you go to the right. And this is, again, one that there's not really work. It's just either remembering that specific fact or remembering the graph of this and knowing that it is leveling off at pi over 2. So the top is heading towards pi over 2. The bottom is a polynomial. Polynomials forget about everything but the big term. X squared is there and there, so it looks like this. So it's going to infinity. So the top is leveling off. The bottom is going to infinity. This is another function that's 0, or limit that's 0. There are 2 more limits I want to do, which are a little bit different. Not totally unrelated, but you want to be careful when you're thinking about limits. So the first one is actually, let's look at this first function and go the other way. So what is the limit as x goes to minus infinity of 2 over e to the x? So what's the limit of e to the x as we go to minus infinity? So for this, again, we can look at the graph here, going to minus infinity, we're going out that way. So in this case, e to the x is going to 0. And the top is just 2. What does it mean if we have 2 over 0? When we look at the top and bottom separately there. So where have we seen this before? What happens if you try to divide by 0 when you're taking a limit? Well, fine, you win. So what is happening here is that it's not this kind of limit. We encountered this thing when we were talking about vertical asymptotes. And when this happens, this means that this limit we're looking at is either infinity or minus infinity. If the top is fixed and you're dividing by smaller and smaller numbers, the fraction as a whole is going infinite. So how we proceeded here is we needed to check, as we're going to 0, are we using positive or negative numbers to do it? The way that we do that here is e to the x is always positive. So when we're computing e to the x, it is going to 0 as we go further and further out, but the numbers are always positive. So that means that this limit is infinity. But this isn't a vertical asymptote going on. It's looking more like this. As we're going, if you look at this function, as you go further left, you're going further and further up. So this is a situation where we've seen how to handle this kind of limits. If the top is a number, the bottom is 0, our limit is infinite of some kind, we have to determine which one, but it comes up in a different way when we're talking about these limits as x goes to infinity. So what you want to start kind of training yourself to do is identifying these forms, these things which aren't numbers, but you see them, and that says, okay, if I see this, then these are the next steps that I have to take. This kind of form, a number over infinity, is nice because it's 0 and you're done. This other form, a non-zero divided by 0, that says your limit is infinite, you have to decide which one. And so being able to understand what to do, even in a slightly different context, because this isn't vertical asymptote behavior, but it's still, we have to analyze it the same way, being able to know how to proceed is important. As another limit, which is kind of strange because it seems like it's in the wrong context, is what happens if we look at the limit as x goes to 0 from the right of x minus 3 over the natural log of x. So if you don't really think about it, this looks like it's in the wrong section, because this is a limit at a point, we're doing limits at infinity. But if you graph the natural log of x and think about what is it doing as you go to 0 from the right. Well, the natural log of x has this vertical asymptote. And as you're going to 0 from the right, the natural log of x is going to negative infinity. It's going along its asymptote down to negative infinity. So here we want to analyze this by looking at the top and bottom separately. The top, you can evaluate it at 0, put in 0 there, and we get -3. In the bottom, you can't evaluate it. You can't put 0 into the natural log because that's not defined. But we can still think, what is its limit behavior at 0? And that gives us this -infinity. So even though this is a limit at a specific point, we still end up with this form number divided by an infinity. And that means that this limit is going to be 0. So another sort of out of context limit where we still analyze it the same way, but you're maybe not expecting it quite as much, so you want to be careful about knowing how to proceed. Questions about either of these two limits? As I guess probably the last kind of function that we'll analyze today is a rational function, which is not so simply handled as these ones we were looking at here. So what is the limit as x goes to infinity of x cubed plus x squared over 2x cubed plus 1? Okay. So the first thing you might try is, well, what do the top and bottom do separately? That's what we did 5 times just now. The problem is that if you just look at the top and bottom separately, they're both polynomials. They're both basically x cubed, and those both go to infinity. And this form, infinity over infinity, is another indeterminate form, like 0 over 0. It was this thing where if that's what you get, that on its own tells you nothing. It could be anything. Lots of different things can happen. And so like 0 over 0, we have to do some kind of algebra or have some way of getting out of this situation. We need to find some kind of cancellation which sort of cancels these infinities, whatever that means. So what we'll do is combine a few things together. So what we're going to use is the previous fact, which is if your top is fixed, your bottom is infinity, your limit's 0. Analogs of limit rules. What I mean by this is we had limit rules that said if you have a bunch of limits that exist and you've added or divided them, you can take the limit of each piece separately and then add them up. That also works if you're taking limits to infinity or a minus infinity. We can't do it yet though, because this is infinity, that's infinity, that's infinity, and that doesn't help us at all. So we'll see exactly how these limit rules show up. The algebra that we'll actually do is going to be factor out the biggest power of x. So we're going to try to get some cancellation. The way we'll get it here is by factoring out as many x's as we can. So what does this actually look like? These are the steps that we're going to use, but how do they actually help us find this limit? So the limit is x goes to infinity of x cubed plus x squared over 2x cubed plus 1. So we'll start with this factoring out the biggest power of x. In the top and bottom separately, the biggest thing is this x cubed. What happens if you factor an x cubed out of the top and bottom? So it all comes down to seeing what is left after you do this factorization. Well, if you factor an x cubed out of this first term, the only thing there is x cubed, so all that you have left is a placeholder 1. There has to be something left because you need a place to distribute it back onto if you were multiplying it out. With x squared here, you're trying to factor more x's out of it than it has. So what that results in is that you're taking more x's out. That gives you kind of a deficit of x's, which is realized by having x's in the denominator. To verify that this is what actually happens, multiply this x cubed back through. X cubed times 1 gives you x squared. X cubed times 1 over x. One of the x's cancels, and you get this x squared back. So if you're factoring out more x's than you have, that gives you, or you do that by putting x's in the denominator. Now the same thing on the bottom. You're factoring x cubed out of this. All that's left is this 2. The second term doesn't have any x's at all, so you divide by 3 x's. After rewriting it like this, the point is now those x's cancel. So the limit of x goes to infinity, 1 plus 1 over x divided by 2 plus 1 over x cubed. This is the place where we can use limit rules because each of these 4 things, the limit of them exists individually. So we can say, let's break this, instead of taking the limit of this thing, let's take the limit of the 4 smaller pieces. So the limit as x goes to infinity of 1 plus the limit of 1 over x divided by the limit of 2 plus the limit of 1 over x cubed. The constants don't go anywhere. The constants are just, those values are the limits. So we get 1 and 2. For 1 over x and 1 over x cubed, those are the kind of limits that we had been talking about. The top is fixed, the bottoms are going to infinity, so those limits are 0. And 1 plus 0 divided by 2 plus 0 is a half. So the very last thing I want to say before you leave, because this is worth saying, this 1/2 doesn't come out of nowhere. If you look back at the beginning, there's a 1 in front of this x cubed, there is a 2 in front of this x cubed, and you have a 1 over 2, which you kind of follow that through, and that's where this 1/2 comes from. So the takeaway is this 1/2 we could have predicted from the beginning, and if I changed this a little bit, really similar algebra would work. So we're not going to do this every time. We're going to see what's the general thing that happens and then use that shortcut. Okay, so that's where we'll pick up next time. I'll see you guys in lab or in class on Wednesday.